So what do we know about the atom? Well, Dalton came along in 1800, and he was really the first one to kind of put down a comprehensive theory of the atom, what we call the atomic theory. He was a pretty sharp guy. He started teaching school when he was a young teenager. In fact, he was a teacher, and did a lot of experimentation with molecules and pressures and gases and all these sorts of things. And what he found was that he could actually summarize what they understood at that time about atoms. And so here's what he came up with. He said atoms can't be divided. In other words, they can't be split apart, they can't be changed, you can't create new atoms. And for the most part, he's right on. For the most part, that's absolutely true. Until you get into nuclear physics or fusion and fission, that's definitely true. Or if you're actually smashing atoms together in a high accelerated or a massive particle accelerator like we can today, for the most part, this is definitely true. Atoms they're just durable. They last a long time. And atoms for each element are unique, he also said. So for instance, all of the carbon atoms are different than all of the nitrogen atoms out there or the helium atoms out there. Atoms are unique. And so, for instance, he would say that all of the nitrogen atoms, for instance, they all look alike, but they are unique and different from all the other types of elements. And for the most part, that's fairly true. However, we'll learn later in this unit about different isotopes and different varieties of, for instance, carbon atoms or sodium atoms and so forth that are a little bit different than the other ones. But for the most part, again, he was right on there. And finally, he said atoms can rearrange themselves into new substances. So for instance, hydrogen and an oxygen, if you get enough hydrogen and oxygen together in the right ratio and give a little energy to it, it can form into a new substance like water. You can rearrange those atoms. And then water, for instance, can join together with carbon dioxide. And plants do this all the time. They take those two things and they turn that carbon and the hydrogen and the oxygen, they rearrange all those atoms into different molecules, such as sugar and extra oxygen. And so any kind of chemical reaction is simply rearranging these atoms into new substances. And he's right on that point. Well, later on in the 1860s, Mendeleev, who is just awesome looking guy, he's Russian, and he came up with an idea. He took all of the elements that they knew of at that time. I think there was maybe 40 some elements that they knew of at that time, all the basic ones, right? Hydrogen and lithium and boron and carbon and fluorine and helium and so forth. And what he did is he started to arrange these things into rows and columns that all had some things in common. And so basically what it is, he organized all the known elements of the time into a table based on properties and their weights. And essentially what he came up with was the very first periodic table. The idea is that it has recurring periods that have things in common. So this column here, or this row here, all has something in common in the fact that they don't really react with other gases very easily, for instance. And you can see that there are a few places where there are some question marks, essentially some blanks in his table. And he didn't actually know all of these elements that we know of today. And what he found was that eventually he thought, we'll discover these elements and fill those gaps, fill those holes. And we did. We eventually did. We found not only filled all those gaps that had the exact properties and weights and so forth that he predicted, but we've also found a lot more since then and extended the table of the elements much, much further. And we're now up into the well into the hundreds in terms of numbers of elements that we've either found or created. Now Thomson came along in 1897, so right at the end of the century there, and he was messing around basically with what's called a cathode ray tube, and basically he was shooting a cathode, or shooting a beam of particles essentially through this tube, and there he applied a electric charge, so a negative charge here and a positive charge here, and what happens is that beam gets deflected. And it deflected towards the positive plate. So what he decided, or what he inferred from this, from the evidence that he collected, was that there's definitely a negative charge. There's got to be some sort of a negative charge in the atom that is pulling that toward the positive plate. And we came up with was what's now referred to as the plum pudding model. Plum pudding was a very popular treat back in the day, and essentially what he said is that there must be something negative in the atom. So we'll call them electrons. They're negatively charged little particles, and he said, I think they're like plums in a positive pudding. So here's what that looks like. He said, I think atoms don't just look like a solid little sphere. I think they look like a positive pudding, in a sense, with negative plums in there. And those negatives and the positive are reacting to this electrical field that I put in here. So a very basic view of the atom, but it was a good start on where we were headed. About 12 years later, Rutherford comes along, Ernest Rutherford, and he starts messing around with his own experiment. And what he gets here is he has a lead box here with a radioactive sample in here, and it's emitting alpha particles, which are essentially positive particles. There are a couple of protons, essentially, that are flying through here and hitting a very, very thin sample of gold foil. And around this thing is a detecting screen that tells him essentially where the alpha particles end up. And what he finds is that most of the alpha particles go right through the gold foil and hit the other side. But every once in a while, a few of them get deflected slightly and hit a little bit off to the side, and even sometimes come back and almost come back to where they started from. And what he says is, dude, this is crazy. This is like firing a bullet into tissue paper and sometimes having it come back and hit you. It just didn't seem possible. It just didn't seem like any. So he checked his results. He checked his apparatus. He repeated his experiment several times. Others replicated it as well. And what he figured was, all right, something here is different. It's not a plum pudding model. Because if it was a plum pudding model, these alpha particles, these little positive particles, would just go flying right through the atoms, like a bullet through plum pudding, essentially. And well, that wasn't happening. So he thought, well, you know what? I think atoms are probably mostly empty space. These positive particles are probably just passing right through the atoms because they're empty space, but yet right in the middle of this thing, there's got to be something, some sort of matter in the middle of an atom that is causing these particles to bounce back. Maybe 99% of the time, at least, these particles are flying right through, no problem. But every once in a while, they get bounced back or deflected, and so there's got to be something right in the middle, and the rest of it is probably empty space. Now, here's kind of what his thought was, is that kind of like magnets, if you have a north and a south pole of a magnet, they attract, right? Because opposites attract, just like Paula Abdul said with her hit song from 1989 called Opposites Attract. However, if you flip the magnet over, and as we all know, if you push two of the same ends of the magnet together, they don't really go together. They repel each other. And so likes, in other words, like things repel. And the same thing happens with electric charges as well. If you have a negative and a positive, they will attract. And if you have two positives, or if you have two negatives, they'll repel each other. And so what he figured was, if I'm shooting positive particles at an atom, and every once in a while one bounces off, there must be something also positive in the center of the atom that it's bouncing off of, or it's getting repelled by. So his idea was that as these positive particles came through the gold foil, every once in a while one would bounce back or get deflected because of this electric charge, this charge of a positive charge. And so he decided, you know what, I think probably an atom is more likely mostly empty space with a positively charged nucleus in the center, and electrons, the negative parts, orbiting around the outside. All right, so positively charged protons are in the center, and negatively charged electrons kind of orbit around the outside. And that must be what an atom really looks like. Niels Bohr came along in 1913, and he was an interesting guy, actually, a bit of a bore himself in some ways. He actually put off his honeymoon to write a physics paper, which later, of course, earned him a Nobel Prize, which was probably worth it. But what he contributed to the model of the atom was the idea that, yes, the nucleus probably contains positively charged protons in there, and that the electrons are actually orbiting around in specific paths, kind of like planets orbiting around the sun. They actually have sort of very specific areas that they would orbit in. So maybe 2 in this first orbit, 8 electrons would be able to orbit in the second orbit, and so forth. And so Bohr really got the idea that electrons are in specific orbits. Now Chadwick comes along in 1932. He's a British fellow, and he starts to go, well, wait a second. We've been noticing for quite some time now, the last 10, 12 years, that the mass of these atoms is just not adding up to what it should be. And what he eventually finds experimental evidence for is that there's something else in the nucleus that's giving it mass, and he calls them neutrons because they have no charge. They're not positive or negative. They're neutral. So there are neutral neutrons in the nucleus. A master of alliteration. So the idea was that the nucleus must be in the center here, and it's definitely has some positive charges in there, these protons, but there's also something else in there that's giving this atom a lot of mass, and so it must be something else. And he eventually found experimental evidence that demonstrated that it was something else. Indeed, it was these neutrally charged neutrons, the electrons still going around the outside in these orbits. Now Schrodinger and Heisenberg, these guys in the 20s, came along. They were trying to figure out where do these electrons actually hang out, and what they determined was that you can't actually find the exact position of an electron. You can only figure out kind of a probability of where it might be. And this is where physics started to get kind of weird, in the fact that we can't really understand or visualize an atom because it's not really like things in the normal sized world. These are things happening at incredibly small scales, and so it's going to look and behave and act a little differently. In a sense, to put it simply, I suppose, you could say that the easiest way to say this would be that electrons are kind of like Roadrunner's legs. Yeah, he has legs, but they're moving so fast that you can't really predict where they're going to be at any one time. By the time you measure it, or if by even the act of trying to capture where something is in this blurry circle, it's changed already, and you're changing it by observing it. And so what they came up with was a fairly uncertain prediction of where electrons would be. And they said, it's not really like a solar system at all. It's really more like a cloud. It's more like a blur. It's more like a region where electrons could be. And so these diagrams here would show that for instance here, that electrons here might be more commonly found right here than they are out here. Or more commonly found, other electrons might be more commonly found here than out here, but you really don't know where it is. And so people would ask, how should we visualize an atom? Is it an orange donut with a blue barbell stuck through the middle of it? No. How should you visualize an atom? These guys basically said you shouldn't. You can't really visualize what an atom really looks like. It just is impossible for us to really visualize this electron cloud. It's really more of a probability, which is kind of tough to handle for us as humans. We like to have certainty, but these guys were all about the fact that it's fairly uncertain. We can predict how it behaves with very high frequency or very high precision, but we can't really visualize what this thing should look like. Now, let's quick review here. So Democritus, the idea of an atom, indivisible particle. Dalton comes along with atomic theory a couple thousand years later. And in the last 200 years, of course, we've moved from this idea of a solid sphere that makes up an atom through the idea of perhaps a plum pudding with positive and negative charges, like so. Rutherford comes along and discovers that no, there's definitely something positive in the very center. We'll call it a nucleus, and that the electrons orbit around the outside. Bohr gets more specific with the orbital paths that electrons take as they go around the nucleus. And Schrodinger and Heisenberg say it's even more obscure than that. It's actually just a cloud, in a sense, of electrons, of where they might be. And then Chadwick comes along a few years later and finally finds proof that there are neutrons in the nucleus, and giving it mass but don't have any charge. And this some of this work eventually leads to the creation of nuclear fusion or nuclear fission, and development of nuclear power, but also of nuclear weapons as well, which had a profound effect just a few years later on the outcome of World War II. Pretty fascinating stuff.